Okay, so let's talk a little bit more about the graphical representation of DFAs. So we draw a DFA as a graph where every state is a vertex. Usually we draw them as circles or disks. Usually the start state is called Q0 or S, that's just a convention. And we mark the start state by having an arrow coming into it. A state is accepting if we mark a fact that a state is accepting by drawing a double circle around it, like here. And now the important thing is that for every state we have outgoing edges. It's a directed graph, and for every vertex in the graph and every letter in the alphabet, every state and every character in the alphabet, there is an outgoing edge labeled with this character, which means that if we're in this state and we read this letter, we move to this the destination of this edge, right? And it's important that all the input character are, for every state and for every input character, there is an outgoing edge, and there is exactly one, right? You cannot have two edges labeled with the same label, because there the DFA has to decide which road to travel, and of course it cannot do that. And in fact, we're going to speak about this, this need to decide things later on in the class. Okay. So that's how you draw it. And the reason why we emphasize how to draw this finite automata is that for many cases, drawing the automata makes it much easier to think about it than, any other description. Of course, later on we will see monstrous example of DFAs where, of course, the only way to do that would be by, defining exactly everything, which would be significantly more tedious and tiring. Okay, now let's see how the DFA works, right? So for example, in the beginning, we're in the start state. We are here. Hello. And now we get the input 0. So we move on the outgoing edge that is labeled to 0 to here. Hello. And now we get 0 again, and we go here, right? So we are now in this state, the state Q2. And now, once we got to Q2, right, we get 1 or 0, we stay in the same state. In fact, Q2 is Hotel California. You can check in, but you can never leave, right? It's, if you want, you can call it a hell state or a sink state. Once you get there, you can never leave. And this is, in fact, quite common to use such states because, sometimes whether a certain condition is violated, you want to reject from this point the input, or alternatively, once a certain condition is met, you want to accept. So then you just send to a sink state, and the sink state can be either accepting or not accepting, and that would be it. Okay, so 0, 0, 1 leads in this case to Q2. Q2. Okay, let's go to the next example. 1, 0. Okay, so we have 1. We're going here, 0, back here, another 0, we are going up here, right, we're following the edges, now 1, down we go, right, so we are back in the start state, and then 0. So we end up in here, in Q1, so this is Q1. Okay. Okay, so which string does this, for which input this automata says accepts? And this is non-trivial to understand. The easiest way to do it is to kind of, essentially by example, right? You start playing around and around and around, and you figure out what string are being accepted, what string are not being accepted, and you can figure it out. Of course, there are more formal ways of doing it, but let's start doing this here, right? So if you think about it, the start state is in the accepting state, right? So So to accept, we need to, so we of course accept the empty string because, we just stay where we are. Okay, now if we accept 0, 1, 0, 1, we go up and we come back, so of course we accept, so 0, 1 is in. And in fact, if you think about it, any repetition of 0, 1 is accepting. Similarly, any run of 1, 0, right? 1 goes here, 0 go back here. So 1, 0 is in. And if you think about it now, this is 1, 0 star, right? 1, 0 star would give me back to the starting state. So at the minimum, we got that all the strings in 0, 1 and 1, 0 star are accepting. Okay, but are there other strings that this would accept? So if you think about it, we allow here intermingling of strings, right? So 0, 1, 1, 0, right? 0, 1, 1, 0, right? This would get us back again, 0, 1, 1, 0. Send us back to the start state. So this is also accepting. And in fact, we can interleave it, right? So in fact, if you think about it, we're allowed to take either any string from here and any string of here and interleave them. So really what this is 0, 1 star, 1, 0 star, star. And if you think about it a bit, this is just 0, 1 plus 1, 0 star. And this is the language of this automata. Okay. Now, can you prove it? Well, yes, we can, but the proof is not going to be very enjoyable, right? Essentially, what you have to do, and essentially that's how all those proofs work, is that you write down regular expressions for all the strings that from the start that arrive to the end state, to each state, and then you use induction on the input string to prove that whatever regular expression you wrote are correct. This is painful, and we will revisit it later on. Okay, now the important thing about DFA is that if I give you an input string, there is a unique way to, from the start state, the automata start eating or reading the letters. Every time it reads the letter, it does a transition, it moves to another state. It might stay in the same state, but usually it moves to a different state until it reaches the end of W, right? So there is a unique destination state that is, I give you the automata, I give you the input, you know exactly which state it's going to end up in. So that's why the word deterministic in the definition of DFAs. Okay. So a DFA accepts a string if and only if the unique walk from the start state when reading the string W ends up in a state that is one of the accepting states. Okay? And the language accepted by the finite automata is just all the strings that it accepts. Now, one needs to be a bit careful about words here. Don't worry about it too much, but the fact that an automata, when we say that M accepts the language L, we don't really mean that it accepts all the string in L. We mean something stronger. We mean that it also does not accept any string not in L, right? So really, the right word we have to use here is recognize, right? The automata recognizes the language. But, usually we'll use the word accept and would accept the impreciseness involved. I'm sure that you're shocked. And that's it for now.